In this problem we are determining how many moles of ions from each of 4 different sources end up in solution. Each one of these materials is an electrolyte, that is, an ionic compound that when dissolved in water produces solvated or aquated ions. If we look at selection A, we have 2 moles of potassium perchlorate dissolved in water. So the name tells us that potassium perchlorate has the formula KClO4. KClO4 ionizes in water to give potassium ions and chlorate ions. So we can write the expression KClO4 solid in the presence of water dissociates into potassium ions, aqueous, plus perchlorate ion, aqueous. It follows that if we have 2 moles of potassium perchlorate to start with, and that the formula has 1 mole of potassium ion and 1 mole of perchlorate ion, that in solution we will have 2 moles of potassium ion formed and 2 moles of perchlorate ion. If we look at choice B, instead of being given the number of moles, we're given the mass of another electrolyte, magnesium acetate, which is dissolved in water. Magnesium acetate has the formula Mg C2H3O2 taken twice. This is the acetate ion. It has a single negative charge. Magnesium ion has 2 positive charges, so it's going to require 2 acetate ions in the formula to balance the charge of the magnesium ions. So we have magnesium acetate C2H3O2 taken twice, solid, dissolved in water, producing magnesium 2 plus aqueous plus 2 acetate ions, C2H3O2 minus aqueous. So we first need to determine how many moles of magnesium acetate there are, and that is a mass to mole conversion. Basically, this requires us to take 354 grams times 1 mole of magnesium acetate over its molar mass, which is 142.4 grams, and that gives us 2.49 moles of magnesium acetate. So we'll put that over here, 2.49 moles. And according to the formula, 2.49 moles of magnesium acetate will produce the same number of moles, 2.49 moles of magnesium ion, since there's 1 magnesium ion in each formula, and 4.98 moles of acetate ion, since there are 2 acetate ions in each formula. Example C starts with formula units of ammonium chromate dissolved in water. First of all, ammonium chromate, from the name, has a formula with 2 ammonium ions for 1 chromate ion. Chromate ion has 2 negative charges. Ammonium ion has a single positive charge, so it'll take 2 ammoniums to balance the charge in 1 chromate. Now our equation then starts with ammonium chromate, solid, and involves that dissolving in water to form 2 ammonium ions, aqueous, plus a chromate ion, aqueous. we'll use the number of formula units to determine how many moles, 1.88 times 10 to the 24th formulas, times 1 mole per Avogadro's number, 6.02 times 10 to the 23rd, and that gives us 3.12 mole of ammonium chromate. 3.12 moles. And when it dissolves, being a strong electrolyte, it will form 2 moles of ammonium ion for every mole of ammonium chromate, so this is 6.24 moles, and 3.12 mole of the chromate ion. In the last case, we are asked to figure out how many moles of ions there are in a solution of 1.32 liters of 0.55 molar sodium bisulfate. The formula for sodium bisulfate, recall that means sodium hydrogen sulfate, has sodium ions and hydrogen sulfate ions. So our equation here is simply aqueous sodium bisulfate dissolving in water, or dissociating in water I should say, to give sodium ions, aqueous, plus hydrogen sulfate ion, aqueous. Now we'll use the information about the volume and the concentration to calculate the number of moles. So 1.32 liters times 0.55 moles in 1 liter equals 0.73 mole. So that's how much of the sodium hydrogen sulfate we start with, and we will get 1 mole of sodium ion for each mole of sodium hydrogen sulfate, and 1 mole of hydrogen sulfate ion. So in each case we need to know the number of moles of the electrolyte that we start with, and the formula tells us how many of the individual ions are formed per formula. And with that piece of information we can calculate the number of moles actually produced.